Hi, my name is Hassan Jansha, and for this video we will talk about question 1, pipeline design optimization for CHEN 3130 continuous assessment 2. So the design statement pipeline states that a water pipeline is to be laid in soil underground. The mean temperature during cold season is 5 degrees and minimum temperature goes down to -5 degrees and exists for a maximum of 48 hours. A design pipeline that can do this while avoiding ice formation while also optimizing pipe depth, underground, and thickness. And some information given to us is the heat transfer coefficient of air at 4.35 and the properties of the soil at thermal conductivity of 0.6, density at 1840, and heat capacity of 2050. For this type of question, it is very important to analyze the design statement. So the main key sentence from the design statement is a water pipeline to be laid in soil underground. This indicates that the pipe will be a semi-infinite solid, which is a hypothetical entity with a singular plane surface that extends in all directions to infinity, in determining the variation of temperature near the Earth's surface. Therefore, from this analysis, we can see that the Earth can be viewed as a semi-infinite medium since the pipe will be underneath it, basically, as well as to design a pipeline that can withstand the cold temperature without formation of ice. We need to ensure that the temperature of the water inside the pipe does not drop below Tx of 0 Celsius. This is to account for the worst case scenario, which is if it's below 0, ice will form, so we will take the temperature of the water as 0 degrees Celsius. Other parameters given to us from the design statement is the infinity or temperature infinity, which is basically the environment at -5, temperature of the soil at 5, time at 48 hours, and as well as said in the design statement, the heat transfer coefficient, thermal conductivity, density, and heat capacity of the soils. To visually demonstrate the design statement, this is on the left hand side what we're supposed to be the scenario where the pipe is underneath the earth, covered all the way around, and this is just a cross-sectional point of view. And on the right hand side is the front view of the pipe with the internal diameter, external diameter, and the thickness indicator over here. And this is the sketch of the design statements, as you can see here, with the temperature of the soil, distance from the surface of the pipe, and the water temperature. Now note that this here is indicated as to show that the soil or the earth is extended in the x, z, and y direction infinitely, since we're using a semi-infinite medium. So the first thing we need to find is the distance from the surface to the pipe as indicated from the design statement. So the distance from the surface of the pipe can be found using the concept of surface convection of semi-infinite solids. Before that, we have to set the boundaries condition of the surface as with the temperature at x, which is the distance from the surface to the pipe, which is infinity, at time t is equal to the initial temperature, and that the heat transfer rate, Qs, as a function of t is equal to the heat transfer coefficient by the difference of, multiplied by the difference of the infinite temperature minus temperature at x equal to 0 at any time t. Now, also, the initial condition here is at Tx, 0 is equal to the initial temperature. So this condition over here and this condition over here as well, if you see, they will allow for the system to be an infinite semi-solid, where we can actually use the following equation for the temperature distribution profile, as you can see here. Now, for this equation, as you can see, there is a complementary error function, which is equal to the minus the error function, as you can see over here. But To find x as seen here, it is very complicated to isolate it and re-manipulate the equation into writing it in terms of x. Although, as you can see in the two graphs, we can still find the error function and the complementary error function from the literature, but it will also still very difficult to do, which now we will explain a different method to do so, to find the x value. So as said in the previous slide, another approach for the distance between the surface of the pipe, we can use this graph over here on the right hand side from the same reference source or the literature data. So we will need to find first the dimensional temperature as well as alpha in both these two cases. So using the thermal diffusivity, which is alpha, is equal to the thermal conductivity of the soil divided by the density of the soil multiplied by the heat capacity, which is equal to 1.591 to the power of multiplied by 10 to the power of minus 7. We find the dimensional temperature, which is equal to 0.5. Note that the temperature here, whether it's used in Kelvin or Celsius, it will also still equal to 0.5. But of course, in other cases, Kelvin temperature will be used. Now, following on, the next thing is finding this value over here, which is the heat transfer coefficient multiplied by the square root of alpha multiplied by the time divided by the thermal conductivity of the soil, which will equal to 1.2. The next thing, therefore, is finding x. So we have this value over here, have this value over here, and now all we need to do is find the x-axis over here. So once we find this, so we drop this line over here, drop it down, it will be equal to 0.2 approximately for this value over here. Now manipulating the equation and writing it in terms of x and filling in the values, we will find that the distance from the surface to the pipe is equal to approximately 17 millimeters. Okay, so trying to relate the data that we just found, or the distance from the surface to the pipe, into a real-life application. Although, based on the Irish Water Code of Practice revision 2 2020, showing different function of pipe and the respective minimum/maximum depth. For example, we have the surface connection pipe as 700 millimeter with a minimum of 600 millimeter depth, housing state with depth of 900 millimeter, water main service with a minimum of 1200 millimeter to a maximum of 3000 millimeter. Now it's very important to note that the value that we just found is not incorrect, but it also means that based on the Irish Water Code of Practice, the 700 millimeter or, for example, 600 millimeter depth is the minimum requirement. But that also does not mean that the value just found, the 70 millimeter, is not wrong based on our calculations. But for a more realistic approach, the pipe must be protected by a reinforced concrete slab of C30/C35, which is the minimum characteristic of cylindrical strength of 30 and 30 megapascals, which is based on the ISEN 206 Irish standards for length, where the depth of it is less than the minimum standards, as agreed upon with the Irish Water Code of Protocol. As you can see, here is also the reference source here. So meaning that to actually try to have a more realistic approach, we can still use the value of 70 millimeters, but we will also require a reinforced concrete, since it's very close to the surface, and in real life application, anything on the surface can causes, let's say for example, a force on it can be too close to the pipe that can damage it. Therefore, the reinforced concrete slab of 30 or 35 megapascal is used to ensure the safety of the pipe. For the thickness of the pipe, to determine the thickness of the pipe, we need to consider the pressure rating of the pipeline, the material properties of the pipe, and the design life of the pipeline. So assuming a design life of 100 years, a pressure rating of 16 bar and 160 millimeter in diameter, and that the allowable stress must not exceed 1/3 of the tensile strength at 420 megapascal according to the European standard EN 454 for PVCA pipes. We can then use the following formula to calculate the minimum required thickness of the pipe. Now, where T is equal to the pressure multiplied by the inner diameter divided by 2 multiplied by SEF. Now, SEF are the allowable stress of the pipe material, the longitudinal joint factor, and F is the design factor. Now, the allowable stress of the pipeline is taken as 25 megapascals. This is related back to the concrete slab. So if the concrete slab is assumed to be on the pipeline, it will be more reasonable to take a allowable stress of less than 30 or 35. Therefore, it was chosen to be 25. The E and F were also set as 1 and 0.5 respectively, also according to the European standard EN 454. Now, plugging in all this information in the equation, we will get the minimum required thickness of 0.01024 meter, which is equal to 10.24 millimeter. We can also find the outer diameter of the pipeline, which is basically the inner diameter plus the thickness, which is equal to 170.24 millimeter. Now, the second video will also relate into this second video, but we will talk about the heat transfer in the pipeline in a bit more details. These are the references used for this video. This marked the end of the video. Thank you for listening.